Today we'll be continuing our unit on AI and machine learning. So today we'll be talking about decision trees. So I'll go ahead and start screen sharing, and William, you can also record this presentation. Here, actually, let me do, yeah. Okay. So can everyone see my screen just fine? Okay, cool. So the first thing we talk about is learning systems. Learning systems to consider information from the solved cases, general decision rules, rules which are implemented in a model which is applied to new cases, different types of models which present their results in various forms. A linear discriminant model would be an example of this, which is a mathematical equation, which you can see below, and presentation comprehensibility. So data classification and prediction. There's two types of data classification, so classification and prediction. Methods of classification include decision tree induction, Bayesian classification, backpropagation, and association rule mining. So method creates model from a set of trained data. So individual data records, such as samples, objects, or tuples. Records can be described by its attributes, attributes arranged in a set of classes, and supervised learning. Each record is assigned a class label. Model form representations. So you have mathematical formula, classification rules, and decision trees. Model utility for data classification include a degree of accuracy, predict unknown outcomes for a new no-test dataset. Classification outcomes always discrete or nominal value, and regression may continuous or ordered values. So description of decision trees, decision rules, or trees. These are intuitive appeal for users, and presentation forms contain if-then statements, which would be decision rules, and graphically or on decision trees. So what do these decision trees really look like? Well, they kind of look like an upside-down tree, or kind of like a flowchart. They're pretty commonly used in programming, even outside of AI. So nodes appear as rectangles or circles, and they represent the test or decision. Lines or branches represent the outcome of test. Circles uh, are terminal leaf nodes, and top or starting nodes would be called the root nodes, and internal nodes are usually in rectangles. So this is what they look like. So this would be the root node, and then they go down to circles, meaning they don't go anywhere from the circle. The circle is kind of the end point, and anything in between would be represented in a rectangular. So one example would be a bank loan application. So to classify this application, we would have an approved class and a denied class. And the criteria, if the target class approved if three binary attributes have a certain value. A, so in order to be approved, A, the borrower has a good credit history, credit rating in excess of some threshold. B, loan amount less than some percentage of collateral value. For example, 80% of the home value when you're taking out a loan for your house. Or C, the borrower has income to make payments on the loan. So possible scenarios, we just take 3 squared equals 8. Equals, there must be an error there. But if the parameters for splitting nodes can be adjusted, the scenarios grows exponentially, as with the square function here. So how do these work? Decision rules partition sample of data, and the terminal node leaf indicates the class assignment. Tree partitions sample into mutually exclusive groups, one group for each terminal node. So all paths have a start at a root node and end at a leaf node, as you saw in the image a couple slides ago. And each path represents a decision rule. joining and of all the tests along the path. Separate paths that result in the same class are disjunctions, ORs. All paths mutually exclusive. For any one case, only one path will be followed. False decisions on the left branch and true decisions will be on the right branch. So now we'll look at disjunctive normal form. Non-terminal node, model identifies an attribute to be tested. Test splits attribute into mutually exclusive disjoint sets. Splitting continues until a node, one class or terminal node, or leaf. Structure, disjunctive normal form. Limits form of a rule to conjunctions, adding of terms. Allows disjunction over a set of rules. So geometry. Disjunctive normal form. Fits normal shapes and decision boundaries between classes. Classes are formed by lines parallel to the axis. Result, rectangular shaped class regions. So as you can see in the picture below, it says the left side shows a simple 2D domain in which two oblique hyperplanes define the classes. The right shows an approximation of the short that an axis parallel decision tree would have to create to model this domain. Binary trees. Characteristics. Two branches leave each non-terminal node. Those two branches cover outcomes of the test. Exactly one branch enters each non-root node. There are n terminal nodes, and there are n minus 1 non-terminal nodes. Non-binary trees. Characteristics would be two or more branches leave each non-terminal node. Those branches cover outcomes of the test. Exactly one branch enters each non-root node, and there are n terminal nodes, and there are n minus 1 non-terminal nodes, just like the binary trees. So our dual goal, develop a tree that is one, small, and two, classifies and predicts the class with accuracy. So a small size. A smaller tree is usually more easily understood. Smaller trees are less susceptible to overfitting, and large trees less information regarding classifying and predicting cases. Rule induction. Process of building the decision tree or ascertaining the decision rules. Tree induction, rule induction, and induction. Decision tree algorithms induce, so what do? They induce decision trees recursively from the root top down. A greedy approach established in basic algorithms include ID3, C4.5. Discrete versus continuous attributes. So continuous attributes, as we discussed in the last meeting, are problems for decision trees. Why? Well, because they increase computational complexity of the task, promote prediction inaccuracy, and lead to overfitting of data. Convert continuous variables into discrete intervals, so greater than or equal to and less than. Optimal solution for conversion and difficult to determine discrete intervals ideal. Size and number. So making the split. Models induce a tree by recursively selecting and subdividing attributes. Random selection, noisy variables, inefficient production of inaccurate trees. Efficient models. Examine each variable, determine which will improve the accuracy of the entire tree. And the problem to this approach is it decides the best split without considering subsequent splits. Now, overfitting, we talked about this, but what exactly is overfitting? Well, it would be the error rate in predicting the correct class for new cases. Overfitting of test data, very low apparent error rate, and a high actual error rate. Now, optimal size for a decision tree, a certain minimal size smaller tree, higher apparent lower error rate, and lower actual error rate. Your goal would be to identify the threshold, maximize actual error rate, minimize actual error rate, achieve greatest predictive accuracy. Now, ending tree growth. grow until the tree grow the tree until additional splitting produces no significant information gain. Statistical test, a chi-squared test. Problem, trees that are too small only compares one split with the next descending split. Pruning, grow a large tree. Reducing its size by eliminating or pruning important branches. Variation. 80% of cases used for training, remainder for testing. Weakest link or cost complexity pruning. Trim the weakest link, produces the smallest increase in the apparent error rate. Method can be combined with resampling. Now, variations and enhancements to basic decision trees. So multivariate or oblique trees, CART, LC, so CART with linear combinations, LMDT, which stands for linear machine decision trees, SADT, which stands for simulated annealing of decision trees, and OC1, which is oblique classifier 1. Evaluating decision trees. Methods appropriateness. So in order to evaluate a decision tree, we look at the method's appropriateness, data set or type, criteria in terms of accuracy, predict the class label for new data, scalability, performs model generation, and prediction functions, large datasets, satisfactory speed, robustness, perform well despite noisy or missing data, and intuitive appeal, results easily understood, promotes decision making. Decision tree limitations. Some limitations of this would be no backtracking, local optimal solution, not global optimal solution. Block ahead features may give us better trees. Rectangular shape geometric regions in two-dimensional space. The regions bounded by lines parallel to the x and y axis. Some linear relationships not parallel to the axes. So conclusions. Utility, analyze, classify data, produce accurate and easily understood classification with rules and with good predictive value. Improvements would be limitations being addressed, multivariate discrimination, oblique trees, and data mining techniques. So that was pretty much the slides for this. And now we'll go over a code model of decision trees. So let me stop sharing and share my screen to the code model. Okay, can you guys see the code model now? Okay, perfect. So right here, I've used Python to make a code model for what we just talked about, decision trees. So we'll go ahead and run this model. And I will show you the output and run through and explain the code. So again, ignore these errors right here, but we still get the output that we need, the intended output. And so our output is right here, as you can see. But it doesn't make any sense now. I'll go ahead and explain what this code actually does. The first part of the code is the data import. As you can see right here, that our function import data. And what this function does is to import and manipulate data, we use the pandas package. So we imported that package up in our import statements. And in this scenario, we're using a URL to fetch data from the UCI site. So there's no need to download the data set. So in order to collect our data for this decision tree, you could either use the URL or from a website, or you can download the whole data set. So I didn't want to download it this time. but I'm using the URL, and the one downside to that would be you need an active internet connection. Whereas if you were to download your data, you could do it offline. So as the data set is separated by commas, so we have to pass separation parameter values as comma. And another thing to notice would be that the data set doesn't contain the header, so we will have to pass the header's parameter value as none. If we will not pass the header parameter, then it will consider the first line as of the data set as the header. So now moving on to the second function I wrote here, the split data set function. So before training the model, we have to split the data set, as we talked about in the slides, into the training and test data set. So to split the data set for training and testing, we are able to use sklearn module. So this is another package I imported. And we use this a lot in this code model for decision trees. I just used pip install with Python to install it. So so we imported that module in, and first we have to separate the target variable from the attributes in the dataset. So that is what we're doing here with the lines x equals balance data dot values and y equals balance data dot values. Right here, separating the target variable. And then the next step would be to split the dataset for its training and testing purpose. So that's the next line of code you see right here. X train, X test, Y train, Y test. Split the dataset, train, test, split, X, Y, test size equals 0.3, random state equals 100. So that line is to split the dataset for training and testing. As we are splitting the dataset in a ratio of 70-30 between the training and testing, so we pass the test size parameter to 0.3. If you wanted to change this ratio between the training and testing set to maybe 80-20 or 90-10, you just pass in 0.2 or 0.1 respectively. So one of the terms we use in the code would be the Gini index, and this is right here, this next function. Second. Okay. So Gini index would be this is a metric used to measure how often a randomly chosen element would be incorrectly identified. It means an attribute when the lower Gini index should be preferred. And sklearn actually used this Gini criteria for Gini index, and by default, it takes in Gini value. And the formula for this index is equal to 1 minus the summation of j to 2. So we're using that Gini index just to see the what was it? Yeah, just to see the inaccuracies, or how often an inaccuracy will come. And now our next function would be right here. So train using entropy. And what this function does is entropy is essentially a measure of uncertainty of a random variable. It characterizes the impurity of arbitrary collection of examples. So the higher the entropy, the more the information content. And there's a pretty complicated formula to that as well, but we don't have to go over that right now. Now we're making prediction and we calculate the accuracy, and we have the driver code below. So for this prediction, we just 1 minute. Yeah. Okay. Sorry about that. So prediction, we are just printing out our values, printing out the predicted values, and then we have another last function, which is to calculate the accuracy. So we use a confusion matrix, and this confusion matrix is used to understand the trained classifier behavior of the test dataset or validate dataset. So now if we run this code, well, so the last thing we have here is our main function, which is basically just running all the functions up here. So now it's a pretty short program. If we run this code, which we did, as you can see, so first it gives us a dataset length, dataset shape, and then our actual dataset, which we imported with the URL. And then we use Genie index, as I explained with the formula. And here would be the predicted values, right? Here it builds the confusion matrix. Right here, it's a bit disoriented, but it says 067. So 3x3 matrix 067, 06718, 01911. And our final accuracy would be 73%, around there. So that base
Question.
yeah.
For data like this, what is the max accuracy you could typically expect with a model?
Well, it could go up to around 80 or maybe 90, but I guess I'd say like this accuracy is roughly normal, and normally it's like good enough unless you're using it professionally. But yeah, thanks for the question. So, does that answer it?
Yeah.
Yeah. So generally, to build on that, it's like quite rare to get like 99 or 100% accuracy, um, due to like it's still AI and it's still it also depends on how much data you're using to train it. Obviously, if you have more data, then you can expect a higher accuracy. But that pretty much goes over all of decision trees, everything I had for you guys. The presentation will be linked up as well as the official recording on our YouTube. And this code, I can also share it with you guys in the Club Updates folder, in the Club Updates channel. So, does anyone have any questions about today's meeting or just the club in general? Okay, I'll take that as a no, I guess. So yeah, quick meeting for today, just going over decision trees. Last meeting was going over regression. So we're slowly just building up the fundamentals for AI. And in terms of future plans for the club, we're probably looking at having a final project in AI, maybe in a couple weeks once we go over a couple more topics with you guys. But I guess that's all I really had for you guys today. You're free to leave and have a good weekend.